the specific capacity to be this, and this, and of course the heat capacity to be this. Now, what then is the relationship between the heat capacity and specific? Like I said, specific is for that of a unit mass. Okay, then heat capacity is for the mass, however, in total. So therefore, we say the specific capacity C multiplied by the whole mass gives us the heat capacity. Okay, the illustration is just simply telling us if the cost of a marker is 500, like I said earlier, okay, and how much would it cost you to buy 10 of them? You simply say the whole number times a unit price. That gives you the price of the whole. So the specific capacity for a unit mass multiplied by the mass, however, tells you that of the whole mass together. So this is a relationship between the specific heat capacity, okay, and the heat capacity. We'll proceed to latent heat. Then I solve the questions right on the board here, okay. Now, I've always said this. The word latent here means hidden, okay, as though it has no effect. One of the effects of heat is that it brings about change in temperature. But in this case called latent, now heat is applied, but yet it looks not visible. That's why we use the word latent heat. And that only happens when there's a change in state. When there's a change in state, okay? Now, for example, if we have ice, okay? Now, moving straight to, without working much, so from here we have Q, the heat energy, okay? To talk about a change in state will be the mass times the latent heat, okay, capacity, the latent heat of that substance. All right, so how then do we define latent heat? Simply defined as the amount of heat energy required to change the state of a body, okay, without a change in temperature. I take it again. It is simply defined as the amount of heat energy required to change the state of a body without necessarily changing the temperature. So that's why it is called latent. Now, let me just paraphrase it. We have these two formulas, so to say, okay, we use in solving most of the questions under heat capacity or latent heat. These are basically the two formulas that are applicable. Okay, now the concept may differ, but still the formulas remains this. So now let's solve this question here. While you see me adopt this formula, okay, and I explain the concept behind it, and I would expect each one of you to do the same thing for this one and put up the answers right there in the comment section. All right, so here, now let's proceed to solve the very first question here right away. Okay, now we have a 40-volt electric heater is used to supply a current, okay, of 12 amperes for 1,400 seconds to a body of mass 1.5 kilogram. At the melting point, the body melts and the temperature rises through 60 degrees Celsius in an extra time of 72 seconds. Determine the first one, latent heat of fusion, and specific heat capacity of the body. Okay, now here, the body was not told us what exactly, but however the case, now we're told here that the body melt, at the melting point. At the melting point, there means that the body, okay, now melted, okay, perhaps from solid to liquid state. Now it melts. The temperature at which it melts, we do not know. We do not know the temperature at which it melts. So let me assume the temperature it melts to be theta degrees. So if it melts at theta degrees, it will also melt to the state, liquid state, and begin the temperature also from the temperature it just left here. So whatever temperature it has here will be the same temperature here as well. So that's why we define it as a change, the heat energy required to change the state, but without changing the temperature. So here we have latent heat here. So now since we are talking about latent heat, so we work with this formula here that tells us that Q equal to mL. Since we notice a change in state, so we're working with this. If there's no change in state, we work with the heat capacity, all right? So here there's a change in state, all right? So the energy here can be energy, however, it can be potential energy, it can be kinetic energy, it can be electrical energy, it can be mechanical energy, it can be energy, however the form. So here we're dealing with electrical energy, okay? Electrical energy, and of course we know that in electrical energy, we have the energy to be current times voltage times time. All right, to be equal to ml also. Here we're giving the current here to be 12 amperes. Okay, the voltage here to be 40, and of course the time through which it melts is 1,400, equal to the mass of the substance that melted, 1.5, multiplied by what we have to find, latent heat of fusion, L. That's what we have to find here. So moving further, we have L equal to 12 multiplied by 40 multiplied by 1,400, all to divide 1.5. Okay, so let's go check rather and see what we've got there in the calculator. All right, so here we have, okay, 12 multiplied by 40, then multiplied by 1,400, okay, 1,400, we've got that to be 672,000, all to divide 1.5. Now let's see what becomes of the latent heat, okay, of the fusion, divided to divide 1.5. That gives us 448,000. Okay, now since the formula tells us this is this, so we've got that to be L equal to Q over M. That tells us joule per kilogram. Joule per kilogram. Joule per kilogram. We may also leave this thing in standard form. Okay, that tells us 1, 2, 3, okay, or in kilojoule as the case may be. So I can leave it in kilojoule to become 448 kilojoule per kilogram. All right. Okay, so we've been able to get the latent heat of fusion of the body to be this, while we proceed to get the specific capacity of the body, okay, on the same platform. So let's see how to get that. Okay. It's just simply based on concept and principle. So we'll proceed. Now here, since it has fully melted to the liquid state, it has fully melted to the liquid state, and at an unknown temperature, which we do not know earlier, but here we're told that the body melts and its temperature rises through another temperature of 60 degrees Celsius. So it became still in liquid form, okay, didn't change state here. It melted to liquid here. Now this is the liquid it melted to. Then the liquid it melted to increase in temperature again, still returning liquid. So, but the temperature at which it increased here, change in temperature here is giving us a 60 degrees Celsius. And so we do not need to bother about the initial temperature. We have been given the change in temperature, however. Okay, meaning that if here was 0, here would have been 60. If here was 10, here would have been 70. Such that the change in temperature already has been given us 60. Okay, now in an extra 72 seconds that it melted. So the time it took it to melt here is now 72 seconds. Okay, all right. Now we are to determine the specific capacity of the body. So here we we do not have a change in state. So rather we recall from Q equal to MC delta theta. All right, we have to find the specific heat capacity, and that is this, C. So we have C, set the formula to be equal to Q over M delta theta. Now, of course, this energy still remains the initial energy, that is the electrical energy we've got there, to be the same as IVT over M delta theta. So the specific capacity becomes the current, okay, from here, the current here, we also got that to be 12. The voltage here remains 40, and of course the time here in 42 seconds. Now, the initial time was the time it took the body to melt. All right. Now, if it melted again in an extra time, it raises the temperature in 60 degrees Celsius in an extra time of 72. So the extra time is what we'll be making use of here to divide the mass, okay, the mass 1.5 times the change in temperature here. The change in temperature already has been given us as 60, and you do not need to convert it to Kelvin. Okay, even though the temperature should be in Kelvin. Anytime you're dealing with difference in temperature, however, if you convert it to Kelvin or not, the difference remains the same. So it's not important you convert, so you leave it at 60. So we've got that C equal to, let's see what becomes of that right away on the calculator, right? So I have 40 multiplied by 12 multiplied by 72. 40, 12, 72, that is 34,560 to divide 1.5 times 60, that is 90. I guess 3 over 2 times 60, 90, okay? So we divide that all together, divided by 90, okay? Here, we've got that heat capacity, specific capacity to be 384 joule per kilogram per Kelvin. So we've been able to solve this right away here. So I expect you, every one of us, to solve the second question, and I'll be expecting the answer right there in the comment section, okay? So, all right, so here, we'll move on to the next topic, and that's going to be on wave. All right, so here I'll be giving us the concept as well behind wave, and I will solve this, and I would expect every one of us to go use this concept I'll be giving us right away here to go solve questions on wave, and on that very day in your physics tomorrow, okay? So wave, quite interesting and simple, okay? Now, in wave, we have two classes of waves. We have that of the mechanical, okay? And we have that of the electromagnetic, all right? So when we say mechanical wave, we mean such a wave that requires material medium for them to propagate. And when we say electromagnetic, they do not necessarily, even though they may travel through a medium, but the medium cannot hold them ransom. They may travel in any, irrespective of the medium. So that's what we mean by electromagnetic. But wave generally means a disturbance which travels through a medium and transfer energy from one point to another without causing any permanent displacement of the medium itself. All right, so here, these are classes of waves. We also have what we call types of waves. Okay, types of waves. Now, under the types of wave, we have the transverse wave. Transverse wave, okay. We have the longitudinal wave. Then we have stationary or standing wave. Okay, let's get this very clear. These are classes, these are types. When we say a wave is transverse, it simply tells us that, okay, we're talking about the direction of the wave itself and the medium. So when the direction of a wave and the medium are perpendicular to each other, then such entirety of the wave is referred to as transverse. But here, when both the direction of the wave and the direction of the medium are in the same phase or direction, we say longitudinal. An example of this is sound wave. Now, sound wave tends to move in the same direction as the air, which is the medium that conveys it. So that's a good example. But transverse wave, here, a good example includes water wave, light wave, and the likes of that. Now, here in stationary or standing wave, when we say a wave is stationary or standing, it means that wave is actually, we actually have two waves traveling in opposite direction of equal amplitude and frequency and combining. Then such combination gives us what we call stationary or standing. It appears though standing. A good example is when you have a string and you plunge it. It will appear as though, okay. Now, actually, it is actually one of them, but the other is a reflected wave, okay, in the opposite direction, having the same properties and combined together, so it appears stationary or standing. Of course, these two can also be called progressive wave. Progressive wave. Okay. Now that leads us to another phase here we need to understand. That's going to be characteristics, okay, of waves. Characteristics of all waves. All waves, however the type or the class, exhibit the following characteristics. Number one, reflection. Number two, refraction. Number three, diffraction. Then number four, interference. Okay, quite interesting characteristics. So let's see them one after the other. When we say reflection, what do we mean by reflection? It simply means a bouncing back of a wavefront after striking a surface. For example, you have this to be a reflecting surface, and the light is incidental this way, okay, known as incident ray. It is bound to bounce back. Okay, so the bouncing back of this wavefront is what we call reflection, and that's what we call the normal. Okay, the normal ray is perpendicular to the interface, to surface of the reflector. Okay, so we call this the incident ray, and of course the reflected ray. All right, so here we have seen what reflection is. Now let's see what refraction is. You're having to take us through this, then I will solve this in a moment. Refraction here, that's exactly the first question here. We have to explain the concept refraction. That's what we have. Now in reflection there is a bouncing back, but in refraction there is a passing through, but a change in direction. For example, you have an interface, perhaps air to water. Now when you have a wave traveling and it gets to the interface of another medium, you don't expect that wave to travel on a straight line. It will undergo a change in direction. Okay, it will either change towards the normal or it change away from the normal, depending on if it is moving from dense to less dense or less dense to dense. But in this case, it is moving from less dense to dense, so it will move towards the normal. So we call this the incident ray. The incident ray, we call this refracted. Okay, since the process is what? Is refraction, so we call it refracted ray. And that's what we call this the normal, then angle of incident, then angle of refraction. Okay, it is from here we've got the Snell's law that told us that the sine of the angle of incident, so the sine of the angle of refraction, is constant for a given pair of media. This is Snell's law, all right, or law of refraction. Okay, now here to explain refraction simply means a change in direction of a wavefront when traveling between two different media because of the change in their densities. Okay, now what actually brought about change in direction isn't because they're going to another substance, another medium. It is actually because the two media, they have different densities. So it is actually the change in the difference in the densities that brought about the change in direction. So that's refraction. Now that leads us to the next question here, critical angle. What do we mean by critical angle? Now I will explain from here as well. Notice this, that this one refracts towards the normal. Why? Because it's moving from less dense air to a dense water. Now let me do it the other way around. Okay, that is dense medium to a less dense. Here you have the incident ray going through a less dense. Now when you have a wave moving through to a less dense, you expect it to float, or rather to move away from the normal. That's the explanation. So this floats this way, which has a high angle of refraction, and this one becomes the angle of incident. All right. Now notice here and the other case. Now when you begin to vary this angle of incident by increasing it, you expect this angle of refraction to also be increasing, so as to maintain the refractive index and to be constant, as the law tells us. So now when we increase the angle of incident, you expect angle of refraction to also increase. Now a time will come when this angle of incident is increased to a point, this refracted ray falls exactly at the interface. Okay, now let me do something here. So I have, now if I have this, the angle of incident is now such that the angle of refraction has now fallen exactly at the interface of both media. Then this angle of incident here is said to be critical. So I can label it as what? Critical angle of incidence. Okay, so that leads us to this. Explain critical angle of incidence. How do you define it? Critical angle of incidence is defined as the largest angle of incident in which the refracted ray is at the interface. okay, or the largest angle of incidence in which the angle of refraction, okay, is 90 degrees, however. Okay, all right. So having said that, we proceed to question number, the 1B said, state two conditions necessary for total internal reflection. What are the conditions? So from here, now here I will proceed. If I slightly increase this angle of incidence, critical angle, by any amount, you expect the refracted ray, okay, now to eventually now undergo full reflection. As I explained reflection to us in the other time, then you will say total internal reflection has occurred. So condition number 1 for total internal reflection means that the critical angle of incidence must slightly be exceeded. Okay, so give them here conditions for total internal reflection rather. Okay, number 1, the critical angle of incidence must be exceeded. Okay, must be exceeded. Okay, then now condition 2 is this. How do I make total internal reflection to occur also? Notice the other case, when it was from air to water, it is such that it moves towards the normal. In that case, you may not have total internal reflection to occur. So it is likely to occur in a case like this where the refracted ray floats, meaning that the light or the wave must travel from dense, as we have here, to a less dense. So that's condition number 2. Light must travel from dense to a less dense medium. Then you can be sure to have the total reflection. Okay, so we'll move with this one here. Then also conditions for interference. What are the conditions for interference? That leads us to the next one here. So I go to interference as a characteristics of a wave. When we say interference, we mean, as the name implies, having two waves, traveling in the same direction and superimposed or placed on each other to interfere themselves. Okay, here, now we simply go here. If I have a wave traveling this way, labeled A, another one traveling this way, labeled B. Now we have this to be an interference. I can also have another interference this way. Okay, another interference this way here, with A, with B. Now these are different types of interference. Interference simply means when two waves, okay, are traveling from the same point of origin and in the same direction such that they are superimposed, that is, placed on one another, then such wave is said to have interfered. So it could be constructive, okay, here, or it could be destructive here. The word constructive there means that the crest of the two waves tally on one side, while the destructive here, the crest of one tallies with the trough of the other one. Destructive here, okay, constructive here. So now that answers the questions here. Interference occur when two waves originate from a common point of source, from a common point here, okay, and they must be in the same direction, all right, and they must be superimposed. So you can pick any of those conditions for interference to occur. So we'll move to the next question, all right, very quickly. All right, so I think I haven't come to this one. Diffraction here talks about the tendency of a wave to bend around an obstacle. Okay, now for example, if you have an obstruction this way such that there's a flow of water within that space, then at the outlet here, you don't expect the water to go directly straight as it was here, or as it is rather. Now you expect the water to bend round this obstacle, okay, that has been obstructing them in this flow. So the phenomenon or the tendency in which the wave bends round the obstacle is called diffraction. So we call this wave here incident ray. We call this one here diffracted ray. Okay, so that answers that very question here. So now we'll move on to the next calculation. Now we need to understand what we call the wave, the model of a wave, very quickly. the model of a wave. Okay, here we have the distance between two successive crests. This is a crest. This is another crest. Successive crest. The distance between them is what we call lambda. Okay, and lambda, in between a lambda, we have a complete circle. Notice this, a quarter circle, and half of a circle. So quarter plus quarter, or half plus half, makes it one. So we can also say that wavelength, okay, is a circle. It's an oscillation. Length of a wave. Length of a complete oscillation. All right. So here, two successive crests of a wave at this speed is this. So this means that the wavelength has just been given us here to be 0.4. They didn't give us directly, but they told us in the meaning. Because wavelength means the distance between two successive crests. We were able to bring that out here. And notice here we're giving the velocity v to be 3.6 meters per second. Then we have to find the frequency. I think this is just a child play. So we recall this wave equation, v equal to lambda f. Now here we have to find the f. So let me make f as a formula. We have f equal to v over lambda. What is the v? 3.6 all over lambda, 0.45. So we have f to be equal to, so then let's multiply that. We have, let's see, 3.6 all to divide 3.6 to divide 0.45. So we've got that to be 8 hertz. So that's the frequency of that wave. That's the frequency of that wave. Okay, we move on to the next question there. That's the D part of that question. Then we'll move on to the next course. Now, we'll move on to the D part of the question here. The question says a ray of light is incident at an angle of 30 degrees at an air glass interface. So let me get that drawn here. Okay, at an air glass interface. Okay, now we have the incident ray. Okay, angle of incident here is given as 30. And I said angle of incident means angle between the incident ray tail and the normal. 30 is here, not here. So we have the angle of incident here. Okay, draw a ray diagram to show the deviation. Okay, now I said I defined refraction for us the other time here to mean a change in direction. So to say a deviation in a direction. So you don't expect the ray of light to go directly this way. No. It will undergo what we call refraction. So it will definitely change by compressing towards the normal because it is moving from less dense to a dense medium. All right. So now we have the refractive index of the glass to be 1.5 here. Now, how do we, they said, draw a ray diagram to show the deviation. Okay. So here, the deviation is going to be, this is the actual line, but it deviated this way. So this angle of deviation. This angle of deviation. This is the angle at which it has deviated. All right. So here, we have been able to draw a diagram here. Number one. Then we have to determine the angle of that same deviation. How do we get the angle of the deviation? Now, let us get the angle of refraction first. Since we're given the angle of incident, okay, angle of incident to be 30 degrees, then we can find the angle of refraction. We will recall Snell's law that I gave to us at that time. That is the law of refraction that tells us that refractive index, okay, let me come here. Refractive index is given as sine I over sine R. But the refractive index has been given us to be 1.5 equal to sine of the angle of incident, 30, over sine R. Okay, so I can find my R by saying that, okay, cross multiply, I have 1.5 sine R equal to sine 30. Of course, we are familiar with the fact that sine 30 is half or 0.5. So I have that to be, okay, let me divide both sides by 1.5. I have 1.5. So I have sine R to be equal to sine 30, 0.5 to be over 1.5. Okay, so I can find for that 0.5 over 1.5, 0.5, that's half, times 3 over 2, 2 over 3, that's 1 over 3. Okay, this is 3 over 2. Okay, divided by 3 over 2. So it becomes times 2 over 3. So that becomes 1 over 3. 1 over 3. Okay, that's 0.3333. So here, I work with the calculator to get the R. R becomes sine inverse of 0.333. All right, so now let's see what that becomes. Okay, okay, let me confirm that. Yes, so we have of 0.333. So we've got that to be the angle of refraction gives us 19.45 degrees, 19.45. Okay, now here we've been able to find the angle of refraction. We have to find the angle of deviation. Angle at which you deviate. So let me come here lastly, okay, and just analyze that for us right away, and we proceed to the very next thing. Now here, now this has just been gotten now as what? 19.45. 19.45. Now we have to find the angle at which you deviate, this D. Now, if it had not deviated, it would have gone directly this line. But unfortunately, it bends this. So this is the angle at which it bends. That's angle of deviation. All right. So here, by mathematical implication, okay, if it had gone very straight line here, we got there to be 30. Now, by that mathematical implication, here is supposed to give us 30. By the law of vertical opposite angles. Vertical opposite angles is 90. Is equal, rather. So on that note, okay, this is it. But unfortunately, the deviation is this way here. So the whole angle together, okay, is expected to be the same as this 30. And meanwhile, we just got the angle of refraction to be 19.45. Therefore, this D becomes 30, which is the whole angle together, okay, minus 19.45. Then we get the angle at which it deviates. Okay, all right, that should be 10.55 degrees. Okay, 10.55. Let me just get the calculator to confirm because we're on the airspace to avoid any unnecessary error. All right, 30 minus 19.45. So that's 10.55. So we've been able to do justice to the questions here, and I expect us to get the principle out of here to solve questions, as many as possible on weight. So I will be putting it to us right here, right away now, that on Tuesday by 5 p.m. African time, I'll be here on the same YouTube channel, and I'll be here live for a math class, math comprehensive class. So I appeal to you, save the date, inform those who are writing these exams to actually be to benefit from this. It's going to be happening live on the YouTube. I hope it's going to be very, very educative for somebody that will stay connected, okay, and save the day, okay, so that you can have such a good and wonderful time right there in your examination hall. So here, I will put a stop right now and expect each one of us to save the date as we'll expect ourselves here, okay, by the grace of God on Tuesday, once again, by 5 p.m. African time. All right, so just before we leave here on the podium, okay, I would ask you, just go right there. It won't cost you anything. Just subscribe to the channel, like it, share it, okay? Thank you. We appreciate each one of you. All right, we await your testimony. Thank you.